Welcome to this explainer. Okay, so how does a fan with literally zero blades actually cool you down? It kind of looks like sci-fi, right? We see these sleek things all over the place, silently blasting air at us, but there are no spinning blades in sight. Well, spoiler alert, it isn't magic. It's actually some absolutely brilliant engineering. So today, we're uncovering the hidden magic of the everyday breeze. We're going to demystify the wild physics and mechanical engineering hiding right inside everything from that mundane household desk fan to huge industrial blowers, and even the tiny cooling systems crammed inside your laptop. Trust me, you are going to look at that everyday appliance in the corner of your room totally differently after this.
All right, let's dive into our roadmap for today. First, we have the anatomy of a breeze. 2. Bladeless and oscillating magic. 3. Axial versus centrifugal fans. 4. The rules of fan selection. And finally, number 5, taking control of speed. Let's get to it. Starting us off with Section 1, the anatomy of a breeze. How electrical energy becomes mechanical energy.
Now, to really grasp how a breeze is born, we literally have to start at the microscopic level, with the electricity coming right out of your wall socket. Inside a typical single-phase AC domestic fan, there's this tiny but absolutely crucial component called the capacitor. Basically, it stores and releases electrical energy. Without this humble little part, your fan would just sit there. It'd probably hum loudly, maybe wobble a tiny bit, but it would not turn. While the motor does the heavy lifting, the capacitor acts like the essential ignition key that actually kickstarts the rotation.
And what's really interesting about this is that the capacitor actually solves a massive physics problem. You see, the electricity supplied to your home is single-phase alternating current. It creates a magnetic field that pulses, meaning it changes in strength but not in direction. Because of that, it provides zero starting torque. The poor motor literally doesn't know which way to spin. So the capacitor steps in and effectively tricks the motor. By storing and discharging energy, it causes the current in the starting windings to be out of phase with the main windings by about 90 degrees. It magically turns a single-phase supply into a two-phase rotating magnetic field.
Let's quickly walk through how this plays out. First, electricity enters the coil. Second, our hero, the capacitor, steps up and creates that 90-degree phase shift, giving us a rotating magnetic field. Third, this shift allows the motor to smoothly convert that electrical energy into mechanical energy. And finally, boom, the rotor holding the blade starts to spin efficiently. Actually, a fun tip, if your ceiling fan ever needs a physical push from your hand to get going, it's highly likely that this exact capacitor has degraded and lost its charge.
Moving right along to Section 2, Bladeless and Oscillating Magic, uncovering clever mechanical engineering.
Okay, have you ever wondered how pushing down that one tiny pin on top of a fan suddenly makes it look left and right? It's like a mini mystery. Inside the gearbox, the fast-spinning fan shaft turns a worm gear. When you push that pin down, a spring forces these tiny ball bearings to engage with the gear system, which slows the rotation way down. This then turns a crank attached to what's called a 4-bar mechanism. By fixing just one short bar in place, the super fast-spinning motion of the motor is beautifully and mechanically converted into that slow, relaxing side-to-side sweeping motion. Just totally elegant engineering.
And that brings us right back to our opening question, bladeless fans. So, the secret? There actually are blades. They're just hidden away down in the base of the unit. A powerful motor down there sucks air in and whips it up into that hollow ring you see on top. Now that ring has tiny slits all the way around it. As the air rushes out of those slits at super high speed, it creates an area of low pressure. That low pressure actually drags the surrounding air from behind the fan along with it. It's a fluid dynamics principle that multiplies the airflow, giving you that incredibly smooth, non-choppy breeze.
All right, Section 3, Axial versus centrifugal fans, comparing the heavyweights of air movement.
So, zooming out from household gadgets, let's look at the two main form factors used in everything from your desktop PC to massive industrial warehouses. On the left, we've got axial fans. Their blades run parallel to the axis, meaning air just flows straight through. They move a ton of air, a really high volume, but at a low pressure. They're generally lighter, cheaper, but yeah, often a bit noisier. On the right, we have centrifugal fans, or blowers. These guys pull air into the center and literally fling it out at a 90-degree angle. This creates a highly directional, super high-pressure airflow that can be forced through really long ducts. They're heavier, for sure, but much quieter.
Just a quick, crazy historical side note here.
The technology behind those axial fans keeping your modern gaming PC cool, that actually traces its lineage all the way back to medieval windmill designs. Obviously, it wasn't until the 1800s that we figured out how to slap an electric motor onto them, but the core aerodynamic principle has quite literally been serving humanity for centuries.
Okay, on to Section 4, the rules of fan selection. Demystifying industry sizing specs. As we scale up to look at entire rooms and buildings, the first major hurdle engineers have to tackle is static pressure. Basically, it's the resistance to airflow in a system, and it's measured in inches of water gauge. The absolute best way to think about it is sipping a drink through a straw. The longer the straw, or the more bends and loops it has, the harder you have to pull to get your drink, right? It's the exact same for a fan pushing air through complex ductwork, past elbows, dampers, and grills. The fan absolutely must be sized to overcome that exact resistance. Then you've got to think about the sound. The industry uses a measurement called a sone. Just to give you an idea, one sone is roughly the hum of a quiet refrigerator heard from about 5 feet away. As you can see, engineers have strict suggested limits based on the space. You obviously can't put a roaring 50-sone centrifugal exhaust fan designed for a loud machine shop into a whisper-quiet conference room that requires a sone limit under 5. The environment strictly dictates the equipment.
But here is honestly the most shocking rule of fan selection. It's a fundamental fan law. Say you have an existing fan and you adjust the pulleys to increase its speed by just 25% because you want a bit more air. You don't just need 25% more power, no way. You need a 95% increase in motor horsepower. Literally, a tiny bump in speed requires a massive, massive leap in energy. And that right there is exactly why getting the initial fan selection right is absolutely critical.
Finally, Section 5, taking control of speed, how controllers manipulate power.
So, we've got the perfect fan, we've beaten the static pressure, and it's perfectly quiet. But how do we actually harness and control its output? Well, we've got a few ways. Conventional controllers use a simple dial to increase electrical resistance, which slows the fan down. The downside? They lose all that excess energy as wasted heat. Not great. Capacitor-based controllers are way cleverer. They change the speed by stepping down voltage without losing energy to heat. Then you have thermostatic controllers that automatically adjust based on the temperature of the room. And finally, there's pulse width modulation, or PWM.
The really crucial thing to know about PWM technology is that digital microcontrollers, like the ones on your computer's motherboard, they only really speak in binary, on or off, 0 or 1. So to control an analog fan smoothly, they use PWM. They send incredibly fast, super short pulses of voltage. By modulating exactly how wide these pulses are, they simulate a smooth analog speed. The physical inertia of the fan just keeps it spinning seamlessly through those tiny microseconds where the power is technically off. It's a brilliant workaround that allows your laptop to instantly adjust its cooling on the fly without burning out the motor.
Wow, okay, we have covered a ton of ground today. From phase-shifting capacitors to the sneaky fluid dynamics of bladeless fans, all the way to the intense laws of air pressure. So I want to leave you with this final thought. The next time you feel a cool breeze from a fan, will you picture the complex mechanics and phase-shifting electricity working right under your nose? I really hope this explainer has given you a newfound appreciation for the brilliant engineering hiding right there in plain sight. Thanks so much for tuning in, and keep asking how things work.